right. Good afternoon, everybody. Thanks for joining us today for another webinar. We're really excited today to have Tim Dunton with Reliability Solutions. Great presentation prepared for you. So we're really excited about that. Before we get started, though, I just want to go over a couple things. We are recording this, and we'll get it up on our website just as soon as we can this afternoon. So if you have to hop off, or if you've got coworkers that should be hearing Tim's presentation, you'll be able to do that after this is finished today. And we also welcome questions. You can type those into the little questions box on the side panel of the webinar, and definitely, send those in throughout the presentation. I'll be tossing those over to Tim. If it's something that we need to kind of have him chime in on before he moves on to another topic, we'll do that. Otherwise, we'll definitely have some time at the end of this to have some Q&A. So feel free to do that. Try and make this as kind of interactive as we can. And, again, I always like to remind, since we are doing this live, just, bear with us if we get any technical problems or audio being weird or anything like that. We'll get that sorted out as quickly as we can. So just like to point that out just in case. And so with that, I'm going to turn the screen over to Tim and let him take it away. So Tim, welcome and thank you. And here you go.
Good deal. Can we all see my screen?
Yes.
Very good, very good. So, hello everybody, and thanks for joining us. This session, I want to talk a little bit about how improving the reliability of fluid power systems. As Maureen says, my name is Tim Dunton from Reliability Solutions, and our mission in life is to help our clients achieve profitable results through excellence in what we call reliable manufacturing. We do that in a lot of different ways. A big part of what we do is, of course, the performance training side of our business, where we've got 4 pillars: effective organizations, which is peoples and skills and methods and things like that. We have craft skills, which is really the domain that we're talking about today, which is the reliability of fluid power. But we also have pillars on asset condition assessment and essential asset care, process excellence, and that type of stuff. But in this session, what I want to talk about is talk a little bit about what the current state of your fluid power systems are and fluid power reliability is, and sort of see if you can relate to sort of some of the things we talk about. And then I want to talk about 6 very, very important elements of making fluid power more reliable. We'll talk about some common failure modes, of course, and then I also want to talk about applying ultrasound to common failures on fluid power systems. Now, for the purposes of discussion, of course, fluid power encompasses hydraulics and pneumatic systems, and I'm sure many of you are already very familiar with utilizing ultrasound and these types of tools around pneumatic systems. So our focus today, even though we're saying fluid power, is really going to be more on the hydraulic side of it. So 2 o'clock in the morning, you've got a hydraulic system down in your plant that's absolutely critical. You're losing production, and you're frantically looking for parts and pieces to replace the pump, because that's the first thing we go to when anything hydraulic stops, right? You don't have it in the store, your supplier doesn't have it, there's no one close by, and operations breathing down your neck. How long is this going to take? I'm sure we've all been here at one point or another. Eventually you end up going to the boneyard and find an old piece of equipment that's got a similar pump on it, and you grab it and then put it in, and once you get the situation sorted, you breathe a huge sigh of relief. But then you are surprised 5 days later when the same thing happens, right? And when we look at fluid power, reliability has never really been a high priority on fluid power systems in industrial plants. And part of the reason for that is I think we manage the reliability by having a very large inventory of spare parts relative to the piece of equipment, and making sure that those parts are easy and quick to change, so that if something breaks, we basically troubleshoot by changing parts till the problem goes away. And while that is somewhat effective. It's a very, very expensive way of doing business, and definitely not very efficient. So when we look at the 6 elements of what it takes to really make fluid power reliable, and we'll get into each of these in a bit more detail in just a minute, but you start with the design, and we'll talk a little bit about that. Precision installation, how we install it, set the machine up, adjust it, and everything is very important. How we commission or recommission after large overhauls and maintenance is absolutely essential. We introduce an awful lot of failures during that process if we're not careful. The other thing is operating and staying within the original operating context. And what happens a lot of times is we'll buy a system to do a certain job, and then after a year or so, we suddenly decide we want to increase the load, or instead of carrying 4 pallets, we want to carry 8 pallets, or something like that. And we never really go back and have a good long look at the detailed look at the design of the system. And so we end up trying to operate the system outside its design parameters. And then we get surprised when things break, because if you're operating outside of operating context, and this doesn't matter if it's hydraulics or any kind of equipment, if you're operating it outside its design context, you cannot maintain your way to reliability, because it will continually fail. So we have to consider that. So that involves some discussion we'll have in a little bit about management of change and how we do that. The other thing is condition monitoring. And when we talk about condition monitoring, the traditional vibration analysis and these tools are available to us. But there are some of these technologies that are very, very applicable to hydraulic systems. And again, condition monitoring really isn't big on the list of things that we do. And then, of course, we'll talk about regular and effective maintenance. So when we look at the 6 elements, it really starts here with the design phase. And in that design phase, we should be developing a strategic plan for the equipment. We should be determining using ASD or RCM techniques or something systematic, scientific way of determining what needs to be done to maintain it. We need to do good specifications. We need to know exactly what we want this thing to do, and the context in which we want it to do it. For example, I may want to operate a rail clamp on a car dumper where I'm dumping coal or iron ore or something out of a car, and that rail dump is going to be operated by a hydraulic cylinder that's underneath the track. Well, in the design of the thing, a good design would be to include things like rod boots and protective things for the rods to prevent ingress of dirt and that type of stuff. A less than optimal design would not include that type of stuff. So we need to think about reliability at the design phase. It's not just about making it strong enough and big enough and bad enough to do the job. It's how do I make it do that job in a reliable way. Also, part of that design phase is procurement. We need to make sure we're procuring good quality products and have good quality standards in place. Precision installation we'll get to in just a minute. That involves assembling the machine correctly, installing it, aligning it properly, making sure we have good standards in that area. And then commissioning and acceptance standards are very important. What is the commissioning procedure that we will use? How are we going to flush the system? What startup checks will we perform? How will we test this to see if it's performing acceptably? Once it's up and running, then, as we operate it, of course, staying with the operating context is important. And of course, throughout this entire period, we should be doing condition monitoring of some sort. And then, of course, we have the regular and effective maintenance. So talking about design for a minute, the critical aspects of design, and this is the same for a lot of machines, not just fluid power, we need to know the functionality. We need to know, what we're designing it to do. And in hydraulics, I need it to perform a task in a certain time period. There's usually the cylinder needs to extend in so many seconds and lift a certain amount of load. And those are pretty well set. And it's fairly easy, given that information, to come up with a proper system. What we don't do, and one of the things that we see happen a lot, especially in hydraulic systems, is in the original design, the designer will have put in all kinds of extra accessories, they're called. I wish they wouldn't call them accessories because they're vital, but they call them accessories. Things like gauges, instrumentation, flow meters. And these are all designed to allow you to monitor the performance of the machine. Either they get left out or they get redlined as part of the bidding process because we want to get the cheapest bid. And when you do that, you end up with a system that you cannot really effectively and efficiently assess the performance. And all of you guys listening right now, think about how many fluid power systems you have in your facilities today that don't have gauges and instrumentation or the ability to assess their performance. It's an astounding number. Sort of along that same line is having access to do condition monitoring. If this thing's in behind cages and stuff that we can't get to, then condition monitoring becomes very, very difficult. So we need access. We also need access for maintenance. A lot of times, especially in larger complex systems, the valve you need to change is always going to be the one in the middle of the machine somewhere where you've got to do a major act of disassembly just to get to the valve. And that makes it difficult. I see some of these systems and they may look good on a CAD program, but when they actually get installed, they're pretty hideous. And then, of course, the quality specifications for your parts. If I'm going to define the performance of a hydraulic system, there's certain principles I need to know. And probably one of the most important principles in the world of fluid power is flow makes it go. And basically, flow in your hydraulic system is what's actually causing actuators to move. Nothing moves unless you have flow. And the speed at which things move and occur is a direct function of the flow rate. And of course, the thing that provides that flow for us is the pump, okay? And pumps produce flow. They don't produce pressure. That's a very, very important concept. What produces pressure in a hydraulic system is the back pressure from the load itself, and of course, any back pressure or pressure loss we get from valves or losses in the system, okay? So if I've got an actuator that's not actuating fast enough, okay, I'm not actuating fast enough, the last thing we should probably do is start playing around with the pressure regulators. But what's the very first thing we typically do, right? Whenever we have a problem with the hydraulic system, let's start cranking on relief valves and pressure regulators. It's not about pressure, it's about flow. Find out where the flow is going, or find out why you don't have the correct amount of flow. So rule number one, flow makes it go. Rule number two, pressure is force. Pressure is force. So the greater the pressure, the greater the force. So if I have a bigger load, then I'm going to need more pressure to overcome that load, okay? And of course, pressure is also related to torque if we're talking about rotary actuators. Now, we combine the two elements of flow and pressure together, and they give us horsepower. That's power. And there's actually calculations you can do based on flow and pressure that will actually calculate how many horsepower how much work you're actually doing, okay? And again, this is a way of assessing pump efficiency. If you know how many horsepower you're putting in, which you can derive from the amp load on the motor and the voltage and things like that, you can then calculate how much flow you're getting out or how much work is actually being done by the actuators, the speed at which they're operating and the volume of fluid you're moving. You then get an indication of how efficient your pump is. So once we've designed it, then we deal with precision installation. And I'm going to go back to the old Nolan and Heath study from the late 60s, which of course apply here in spades. And I want you to look at that one in the bottom right-hand corner down here, the pattern F failure, because remember, 2/3 of all our failures are pattern F type failures, meaning there's a large amount of infant mortality. And when it gets to fluid power systems, infant mortality is where most of those failures occur. And particularly if I'm in the habit of dealing and troubleshooting by changing parts and pieces. Remember, as soon as I change a part, a pump, a regulator, directional valve, whatever it is, and put a new one in there, I'm subjecting myself to the same infant mortality. And so on we go with these failures that don't need to be happening because we're not really truly getting to the problem. So this is really how parts fail. Of course, when it comes to mechanical failures, you're probably all familiar with this. We talk a lot about the unbalanced alignment assembly type issues. And in the world of hydraulic systems, people say, well, how can misalignment be an issue? Because I'm using a C-face mount, and most of you are using some kind of C-face adapter for your hydraulic systems, and people say, well, there's no way to do anything with the alignment, and that's actually not true. We see a lot of these little pumps, such as you see on the screen now, that are actually misaligned, and there's several ways that can happen, but a lot of it has to do with the machining of these bosses and the machining of the frames and things like that. Very hard to do much with it once it's misaligned. So the way to check this is with some good, healthy pre-alignment checks. And one of the things we should be doing with these C-face mounts, before we place the motor on its distance piece, we should check runout. We should check the face runout. As you see here, we've got a little last word indicator sweeping the face to make sure the face is true to the shaft. We should check the bore run out of this C-face here, this register fit right here. That needs to be correct. If that's not correct and true, then this whole motor will be offset. So you'll have offset misalignment. The face here, if it's not true, gives us angular misalignment. I've seen a lot of these where these can be 20, 30 thousandths of an inch off from the manufacturer in some cases. And so at that point, you end up in a situation where you start to wear out your couplings prematurely, obviously damaging the bearings in the machine, both the pump and the motor itself. The other thing you can get on this face as well is a condition that's similar to soft foot. And those of you who've done some alignment in the past or are familiar with soft foot around the feet of the machine, but you can also get a similar effect on this face, which distorts the motor and causes motors to overheat and that type of stuff. So once I've installed it, the next thing I have to do is commission it. And in commissioning, we can certainly destroy the machine as part of that process. An example of that is maybe I'm bumping the motor to check for rotation. Of course, it's a C-face mount, so it's extremely hard to split the coupling. So I bump the motor and get it wrong. Now I run my hydraulic pump backwards and dry, basically. Even for a few revolutions, that can cause scoring, which will lead to damage. Most, heck, you can even get it on Amazon now. You get yourself a phase rotation meter. You don't need to bump the motor. You can check for phase rotation ahead of time, make sure the motor is going to be running in the correct direction. But anytime we starve it, anytime we put air into the system, and of course the other thing during commissioning that we don't do a good job of is cleaning the system after building. And making sure that the fluid conductors themselves, the pipes and tubes, are all properly cleaned out. And that just doesn't mean throw a bit of oil down them and see if they're clean. We should be sending a pig. There's a couple of companies sell these foam pigs that will actually go out and scour the inside of the pipe and make sure it's perfectly clean to eliminate contamination. Because as we'll see later on, contamination is a big issue. And again, it's the major source of pump failure. If you talk to any of the big hydraulic manufacturers, the number one cause of issues is always going to be contamination. When we get to stay within in operating context, and again, this is all about defining what the operating context is, what we expect this system to do, but then it's very important that everybody understands those are the limits. Now, if I don't have gauges, and I don't have flow meters, and I don't have these accessories, as they're called, it's going to be very hard for me to tell if I'm actually operating within the operating context. So without gauges, it can be, you're almost like you're flying blind, okay? And so having the gauges in place and making sure we monitor pressures and flows, I think about a rotary actuator like a Haglund's drive. We should have a monitor of the amount of flow going to the case drain, because that's one of the ways we tell how much wear we have. The other thing, and that's why it's in capitals here on this slide, that we have to be careful of is we have to ensure that any changes to the operating context of the machine, in other words, if anybody wants it to do something different, they are identified and communicated and then go through a process to validate that that can be done. Again, system creep is a big issue, not just in hydraulics, but in any kind of fluid power system. So the next item we have on our list is condition monitoring. And of course, one of the most simple ways of doing condition monitoring on any system is of course visual inspection. And certainly I get involved in doing a lot of walkthroughs and a lot of assessments in terms of reliability. And you can pretty much walk through the basement of the plant or an area of the plant, and just by looking get a pretty good handle on what kind of state they're in reliability wise. So when we have condition monitoring, just the visual inspection itself can tell us a lot. But visual inspection and hand feel, they tend to be what we call late stage indicators. And depending on the criticality of the piece of equipment, of the hydraulic system, where it fits in your system, depending on how complex it is, depending on lead time for parts and things like that, that simple visual audible inspection, tactile inspection by an operator may be all you need. As the machine's criticality increases, then it behooves us to get earlier warning, and that's where we can use some of what we call the midterm indicators up here. Things like infrared is a very powerful tool for troubleshooting hydraulics. We'll get to that in just a minute. Heat is a very, very important indicator. And then the sort of early indicators like oil analysis is probably the biggest one you have for fluid power. Vibration can be a little bit tough sometimes because by their nature, positive displacement pumps tend to put a lot of pressure pulsations into the system, which sometimes drowns out some of the subtle early changes that you'd see. It's possible, it just takes a lot of work, but I tell you, ultrasound here is a really, really good tool in a lot of different ways. And again, towards the end of this presentation, I've got some examples of that and some applications of it I think is really, really powerful. I guess the point I'm trying to make is condition monitoring is possible to do on hydraulic systems. Okay, we don't have to just run them to failure. We can do condition monitoring. And of course, also wrapped up in that condition monitoring is performance monitoring as well. Looking at visually, again, you guys don't need me to tell you what good looks like. I don't have a whole bunch of photographs here of good and bad. I think we all recognize what good and bad looks like, but general cleanliness, obviously, if it's dirty, covered in dust or stock or ore or something like that, then it becomes very difficult for heat to transfer out. The other thing, and if it's a very dirty environment, then it's not, that environment is not cleaned up. Then anytime you open up the system to top up with oil or change a filter or something, you're going to get all kinds of dirt ingress into your system. Obviously, oil and fluids leaking around the machine are useful. Talking to one of our fluid power instructors the other day, and an old school way that I used to do when I was growing up looking for leaks on fluid power, very small leaks, is we take toilet tissue and wrap it around the fitting, and the osmosis of the tissue would actually draw any oil out there. So even very, very small low-grade leaks we were able to identify. Of course, today, that was old, back in a long time ago, of course, but today, I don't know whether that would be allowed with fire protection and stuff like that, but it was a pretty good way of determining leaks. If you have to wade through ankle-deep hydraulic fluid to get to the machine, maybe we need to try to fix that so we can see where these leaks come from. Local instrumentation, of course, and as I said earlier in this presentation, one of the things that we are very, very weak at is providing good instrumentation to allow us to assess the performance of our machine. And this doesn't mean I've got to go put gauges everywhere, because as soon as you put gauges everywhere, then now you've got to maintain those gauges and they get covered in dirt and broken and busted and everything else. But at least have the pressure ports to be able to install a gauge. And so what a lot of our clients are doing these days, instead of installing gauges out there, they'll take one of these little mini mesh connectors or quick connectors, and they'll put that at the strategic places they need it in the system. And then they'll keep a nice set of gauges in the shop, and when they need to go out and take a look at what this machine's doing, they'll take the gauges out, plug them in, take their readings, and then remove them again. And that's relatively inexpensive way of doing of getting that information. And obviously things like, depending on where you are, corrosion, looseness, and signs of overheating are all pretty obvious stuff. Flow makes it go. So with a positive displacement pump, the amount of flow you get is directly related to the speed or the rotational speed of the pump. So taking a tack or a strobe or something out to measure the speed of the motor, measure how fast the pump is turning, and validating that's within specifications is a very important step in troubleshooting fluid power systems. One of the first things I'm going to do is what speed's it turning at? Is it at the right speed? Especially nowadays, as we've got a lot more variable frequency drives and things like that can fail, and we can have issues in that particular area. Again, $500 for a little Monarch strobe or something like. Well, you don't have to have a Monarch, but any kind of strobe is a very, very worthwhile investment. Of course, if it's bundled with another instrument, you don't have to carry two things around. So much the better. In fluid power systems, the third principle, we talked about flow makes it go, pressure is force. The third principle that we have to consider is heat. Follow the heat. Whenever you're troubleshooting fluid power, we follow the heat. That'll tell you where the problem is. The way it works, and it basically goes back to Isaac Newton. If I've put a bunch of energy into this liquid, it's at a high pressure, so it has high potential energy. If that liquid goes to a lower energy state, okay, in the process, it's got to do some work. And if it's not physically moving anything, then you can't destroy energy, you can only change its state. So if it doesn't physically do any work to move something, the energy is dissipated in the form of heat. Okay, so whenever I'm troubleshooting a hydraulic system, one of the first things I'll either have a spot radiometer like you see on the screen here in your hand, or I'm going to have an infrared camera. And again, Amazon or little FLIR one, you can turn your iPhone if you want into or the FLIR 2C. These little simple pocket-sized $300, $400, $500 infrared cameras are just perfect for this. You can go out and you can look at a system really quickly, and you can see which of the valves is dropping all the heat across. And if that's a relief valve going to the tank, we have to ask ourselves, why is that relieving back to the tank? Is that the correct operation? What's my operating context? And certainly if you've got a pressure compensated pump, which varies the flow rate, right? And you're dropping a significant amount of heat across a relief valve, that's a flag. That shouldn't be happening, because your pump should be going off stroke to reduce the flow. And how many times do we complain or do we get reports that my hydraulic system runs hot and it's overheating? And the first reaction to that is to try to add another cooler to it, or put a hose on it to try to cool the reservoir, or a variety of other different things. And we never ever go back and ask ourselves, why do we have the heat in the first place? If the system is properly designed, and to be fair, most of them are, and we're operating it within its design specs, then the normal temperature for a hydraulic system reservoir should be 80 to 150, maybe 130 is optimal. Don't want it too low, we don't want it too high. If your system's running hot, there's a reason for it. Obviously, if it has a cooler on it and the cooler's plugged, then that's a good reason. But in many cases, it's got a cooler on it, but we decide that the designer didn't know how to design properly, and the cooler's inadequate, so we add an extra cooler instead of doing what we should do, which is trying to find out where the heat's coming from. And again, anytime we're doing work, or we're dropping oil from high to low pressure and not doing effective work, then we're wasting heat. Oh, by the way, the energy to create that heat, you're paying for. So in terms of energy costs, not only are you causing reliability problems because you're overheating the machine, you're also paying to do that, which doesn't seem to make a lot of sense. A couple of little sort of fuzzy infrared images here. Again, looking at a big hydraulic system, you can see where the heat flow goes. I use infrared to validate that my filters are operating correctly. You can definitely see if a filter's in bypass and plugged, because the bowl of the filter will be relatively cool compared to the head, where it's all going across the head. So many uses for this. And with the cost of this type of tool, the imaging tools coming down so far to where they're pretty affordable, I don't know why we would not have something like this. The other advantage of infrared is in some respects it's a standoff weapon, isn't it? Because increasingly we're putting cages and perimeter guarding around our equipment, which makes it increasingly difficult to get in there and physically touch the machine or do a conventional vibration route, which makes it, sometimes we don't do the proper correct amount of condition monitoring. Whereas with infrared, I can be some distance away and still capture the heat. So what do you monitor? This is not by any means a comprehensive list, but these are some of the things that we should be monitoring fairly frequently. We've got the temperature, we've got obviously oil level and condition, suction pressure, discharge pressure, and flow. Remember, flow is a very important parameter. The global machine cycle time and the cylinder extend times. And we just do that quite simply with a stopwatch. Some of your things like Pi and your historians and things like that will probably even be able to capture some of that information for you. If it's a hydraulic motor, then we can capture the speed. If it's only turning at 282 RPM, which it shows on the screen, chances are you're not going to use a strobe for that. That'll be pretty tough strobing down at that slower speed, but you can easily get a hand tack that will do the same thing. As I say, ultrasound is a very effective tool around fluid power systems. I'm not going to go into all the details on how it works. I'm sure most of us on the call, being as it's a UE thing, will probably already know about this. But in terms of bang for the buck, there's got a whole lot of value around fluid power, in my opinion. Not just obviously on the pneumatic side for air leaks and all that. That's already well documented. The thing we have with air leaks is, it's easy to document. On hydraulic systems, external leaks are fairly easy to document too, because there's oil on the floor, right? Don't necessarily need ultrasound to document that external leakage. But on the operational troubleshooting side, and particularly both pneumatics and hydraulic systems, I believe there's a great opportunity there that we're not using. We've done a fair bit of work on this over the years in using this technique to really troubleshoot operational type issues on fluid power systems, both pneumatic and hydraulic. And most of that involves using the contact probe and probing around various critical parts of the system, like directional valves and relief valves and isolation valves in some cases, filters and that type of stuff, to try to determine if you've got any internal leakage. And just as you check, for example, steam traps with ultrasound, a similar kind of technique for fluid power, because essentially we have a gas that's going from a high to a low pressure across a small orifice, the leaking valve, and it creates turbulence, and that creates ultrasound. And then through the magic of mode conversion and all that kind of stuff, if we get that contact probe in the right place, we should be able to detect it. A lot of times it's more of a comparative type thing, where knowing what a good one sounds like and knowing what the bad one sounds like, rather than necessarily something that's quantifiable. Oh, I've got, with the external leaks, so many dBs means so many CFM. We're not kind of doing that. And with bearings, your 8 dB rise means you got to lubricate it. It's not necessarily quantifiable, but certainly being able to identify when that leakage is there, it can bring a lot to the table. Again, in the world of go back a slide here, in the pneumatic systems, I did some work a bunch of years ago at a facility where they made ends for beer cans, the tops for beer cans, and that's a fairly involved process. They bring a strip of it's probably a couple of feet wide of aluminum of the right thickness in, and then the first step in the process is a stamping press, which stamps out the blank. And then there's like 7 or 8 different operations on that head, on that lid, to form it, to make the shape. They have to score it for the ring pull. They have to put latex on it, and a bunch of different stuff goes on. And all of that is automated. So your operator basically presses the button, the stamping press rolls, and all the operator does essentially is take the stacks off the back end of the machine. So there's a lot of pneumatic pick and places going on, and obviously the timing has to be pretty good, because when you're stamping, your press is running at 360 strokes a minute. You got to get in there and snatch that little piece of aluminum out there pretty quick. And if anything kind of misfires, the results are usually pretty spectacular. It's like little ninja knives flying everywhere. Anyhow, that whole process for each line was controlled by I want to say about a 3 foot by 3 foot pneumatic panel with a bunch of solenoids on it, and basically directional control valves, fully automated. And when they went in the hay and they had a problem, the standard practice that they developed was to change that whole panel. It was quicker to do that than try to troubleshoot it in place. So I don't know whether you can imagine the amount of time it would take to change that panel, how many dozens of connections they have on the back of that panel to take it off. And of course, they had a brand new panel or a rebuilt panel in the shop ready to go. So, at least they had that. But it was costing them a bunch of downtime, and it was many hundreds of thousands of dollars worth of downtime at the end of the day. We were then there doing some training for their operators, and started using an ultrasound gun to see if we could detect a problem. And when they had a problem with a unit, I got out there and was able to use the contact probe on each solenoid valve and just listen. And you'd go along the line and you'd hear, and you'd come back to it, and there was the one solenoid valve that was passing. So one 7/16 Allen screw later, a couple of O-rings, we replaced that one solenoid and they were back up and running. And so after that, they actually instigated a practice where they trained the operators to use, and I think they were UE 100s at the time, it was a long time ago now. They were just using UE 100s. And so when they had a misfire or something wasn't working right, they'd go listen to this and they'd pick out the right solenoid and save them a bunch of money. So, in terms of operational troubleshooting, that's a pretty useful tool. There's lots of ways we can use it. When we talk about the hydraulic things, the things that we can work on here for hydraulics is obviously internal leakage of valves, and whether that's a relief valve or whether that's a directional control valve that's not passing properly. We can listen to accumulator operation, particularly piston accumulators, rod misalignment on cylinders. Jackknifing is a major cause of failure and reliability problems on both pneumatic and hydraulic systems when the rods are not lined properly. We see that clevis there. We assume it's self-aligning, but it's not. That'll cause rods to break and, of course, seals to wear. We can actually hear that. Those of you that may have rotary actuators like Haglund's drives, those very slow rotary actuators, picking up internal leakage in those early on is pretty easy to do. And then the usual stuff, the usual suspects like cavitation, air entrainment, and as I said earlier, filter bypass. Typically my setups here, I'm going to use the contact probe, and I know that for valves you're supposed to use, I think, 30 kilohertz or different things. I've had really good luck just sticking with the standard 40 kilohertz and listening to valves. When you're on a directional control valve, you need to see what the schematic or the section of the valve looks like, and of course you want to try to physically get as close to the valve seat as you can, because obviously that's the bit that's going to be leaking. In some cases, on the low pressure side of the system, on return lines and return filters, downstream on the tubing is usually pretty good. Remember, a lot of your low pressure hydraulic piping is thin wall tubing. So with mode conversion and what have you, you can actually get a pretty good signal right off the downstream if it's leaking, rather than actually on the valve itself, which tends to be a thicker wall and perhaps not quite as easy to do, especially when you've got blocks and cartridge valves and things like that, where you've got a bunch of valves in a block. It can be a little tricky at that point. So let's talk a little directional control valve here. Normal operation, when it's passing, you're going to hear kind of a white noise, and I've got some examples of the sounds coming up here in just a minute. But the important thing is you should get a clean cutoff. If when it's cut off you're hearing any kind of crackling noise, or you're hearing hissing indicating leaking, then obviously you've got some leakage. So let's take a listen to this. Hopefully the speakers will work for you. you hear it on the leaking one there, you heard a little bit of a tonal quality when it was passing, and that was just, it was on a different pump that was putting out some vane pass, and we got that. But the important thing was the crackling that happens after it's supposedly shut off. That's your internal leakage. Okay, so that's a directional control valve. A relief valve, again, knowing what normal operation is and what abnormal is important here. So let's have a listen to that. Starting to open now. Wide open and then fully closes. Now let's listen to it again. Right there where you've got that crackling, that's where it's starting to feather. So a relief valve should either be open or closed. And so if you come up on one that's got that crackling, then it's feathering for some reason, or is it leaking? Okay, combine that with a infrared and look for heat. You might find out where your flow is going, so your machine is not going. Accumulators, a couple of types of accumulators depending on what you have. Probably I think the most common type typically is going to be the bladder type, where we have a bladder here, rubber bladder inside a chamber that's filled with an inert gas. Hydraulic fluid here pressurizes the bladder and compresses the gas. A loss of system pressure results in the bladder pushing the fluid back out into the system. These are difficult in any situation because picking leakage here in operation is not hard. It's not easy to do anyway, and usually just involves checking pressures and things like that. And even with ultrasound, I haven't had much success doing anything with that. The piston type, again, this is a case of what does normal operation. Typically what I've got here is a piston. This is the gray part here. Oops, just go back a little bit. This gray part here is the piston, and this is the gas area. This is the fluid area. So as the fluid pressurizes and compresses the gas, the piston moves up, and as the fluid then exits, the piston goes down. So these tend to be larger on larger systems and high-powered, high performance, but because I've now got motion, I should be able to hear something. So let's take a listen to this one. So what you're listening to there is the cylinder that had lost the gas charge, and the only reason we knew that is it was different to the others. So in this particular rig here, you've actually got 4 accumulators, and these were actually on a system that was running a pressure diffuser at a pulp mill. So they have hydraulic pumps that pump these things up, and then when they want this diffuser to move quickly, they discharge these accumulators. So they have that cycle that you could hear. And they'd been having trouble. The diffuser wasn't moving the right way, and we went around and started trying to help troubleshoot them. And we're just listening basically at the midpoint here with a contact probe, and we noticed 1 out of the 3 sounded weird. Again, confirming that with some infrared, we saw some excessive temperature, and then when they went up top with the gear, they have to shut the machine down, but they then realized that they lost their gas charge. So again, a simple little troubleshooting tool there for accumulators. Common failures we see on cylinders, on linear actuators and cylinders, is jackknifing is probably the most common, where we're putting side loads on this rod, and basically that side load will take the seals out. I've got an example here of that. So when you hear the normal operation of that thing as it extends and retracts, it's a pretty quiet thing. And we're listening right now. If I go back one slide here, hang on a second. We've got the contact probe right here, right above the seal, is where we're trying to listen to, some point of contact. Sometimes you may have a cushion in there. That's probably not the best spot. You really want to be right here on the seal, or even on the wiper if you can get to it. And you'd heard when it was operating normally, there was almost no sound. But then when we put a 25-pound side load, which really isn't a lot of load when you think about it for a misaligned cylinder, we could actually just hear the seals rubbing. So again, this would be a case where you could do some comparison. This is what normal sounds like. This is what abnormal sounds like, and be able to identify a pretty serious problem. Of course, if you leave that alone, then you end up wearing the rods and seals and getting leaks again. Some of you may have these. We call them Haglund's drives. I guess they're owned by Rex Bosch now, I suppose, but it's a trade name. But these guys make a rotary actuator, and the whole purpose of this is it's a very slow speed actuator. You don't need a gear reducer. It's very controllable and produces a lot of torque. And the way it works is hydraulic fluid comes in to the ports in here. That fluid is then pressurizing underneath these pistons. These pistons have a roller follower that goes against the cam shape in the casing. So as this piston extends, that roller follower follows that cam and causes torque and rotation. One of the key elements of this unit is it has to leak to lubricate itself. So these pistons are designed for a little fluid to go past the pistons, and that's actually what's lubricating the rest of this thing. That is taken away by this pipe right here, which is a case drain. By the way, I'm not happy about that flow meter on that case drain. One of the things you've got to be careful of is you don't want to put any back pressure on this casing at all, otherwise you cause all kinds of havoc inside. If that's the correct flow meter, if it's a very, very low resistance flow meter, that's okay, but it kind of looks like a standard one, but that's another story. Anyway, one of the ways of monitoring if you have wear is exactly as you see here, this flow meter on the case drain, and when that gets above a certain level, then we know our internals are worn out and we need to replace. If you've got a flow meter, that's nice. I don't see too many with flow meters. An old way used to be you'd break the line, put it in a bucket, and calculate that. But obviously that's a little fraught with danger as well. So we were at a facility that had, and I don't remember how many of these things, but they had 20 or 30 of these things. And the way they plumbed them in, which wasn't really great, but it was the way it was done, was they all came to a common case drain eventually back at the reservoir. So you couldn't really tell which one was leaking. So we went in with ultrasound. Let me just stop that for a minute. We went in with ultrasound and started listening. And really, I'm just putting the probing around on the casing here, somewhere on the axial right here is not a bad place to be, out on the periphery. So you're sort of out in this region out here, which is where the leakage would be occurring. And here's what we got. Pretty obvious. And what was interesting in this case was that of the 20 or so of these things, they had about 4 of them that really weren't doing any work because they were leaking so badly internally. So again, another indication, again, know what good sounds like and then know what bad sounds like. Cavitation, we use this on regular centrifugal systems, but I've got an example here of that. A lot of times you don't necessarily need ultrasound for this. If you've got a pump that's cavitating, you can pretty much hear it. It's pretty loud. However, if it's in a noisy part of the plant or something, you may not hear it directly. Again, that was taken off the inlet tube or the suction tube to the pump. You can definitely hear the crackling and the hissing there. Aeration sounds a little similar, but a little more crackly. See the air bubbles coming in? When they hit the pump, you can hear the little crackle. See that crackling sound is every time an air bubble. Of course, once one of these big bubbles slugs in there, it's a problem. And again, cavitation, aeration are major causes of pump failures and problems in hydraulic fluid power, breaking down the oil film and causing excessive wear and damage to our internals. Couple of different types of filters. Of course, we have the the pressure side filters, we have return filters, and of course the major issues is when the filter gets dirty or it's actually in bypass. So every filter up in the head of the filter will have a spring-loaded bypass valve to protect the filter. Once that filter's in bypass, it's no longer filtering for you. So this is a low pressure filter, normal operation. And basically, I've got the contact probe here on the head of the filter. And what I'm listening for is that relief valve open? Pretty obvious when it goes into bypass, eh? So that's on a low pressure filter, on a return line filter. I think I've got some more on a high pressure side over here. What we're listening to there is listening to the head of these bypass filters that you saw in the video. And what was happening is this was on that same system with the accumulators. Is when this pressure diffuser fired, there was a tremendous amount of flow through the system. And the flow was too much for these filters, and so they went into bypass. What had happened here is the system originally was designed correctly, but they'd upped the stroke rate and done some other things to the diffuser. They never upgraded the filters. So in terms of filtration, these things were pretty much useless because whenever you were putting fluid through them, they went straight into bypass because we just got too much flow. Okay, and again, we were able to detect that using ultrasound as well. So that's the condition monitoring side of this thing. When we get into regular and effective maintenance, again, I'll go back to our condition monitoring. We need metrics and measures. And again, you've got the sort of day-to-day stuff as we looked at earlier, which is just temperatures, flows, level, pressures, cylinder extension time. But then you have some more strategic type measures month to month, and that's whether we're completing our routes on our hydraulic systems, making sure we have good ISO cleanliness targets. I'd say personally those are a little high for my taste for a hydraulic system, but it just depends on where you're starting at, right? Operating temperature, operating flows, pressures, motor amps, motor leakage, and that type of stuff. That would be, of course, a hydraulic motor leakage at that point. So those are some of the things. So to kind of summarize what we've talked about, the traditional method for troubleshooting fluid power has always been, change parts till the problem goes away. Or we do some kind of scheduled replacement where we replace all the directional valves once a year. And remember, that works for time-based age-related failures. The problem is most fluid power failures are random in nature. Therefore, some kind of condition monitoring is required. And using ultrasound can certainly sort of help us in that area. So. That's all about all I've got. You can contact me the info up on the screen here. You see my email address there and our website. Also, a little shout out to a new product we got coming out here in September, which is called Reliable Manufacturing on Demand, which is a sort of online training, all related to reliable manufacturing and all kinds of good stuff in there. Anybody got any questions?
All right, awesome, Tim. Thank you so much. That was great. So no questions yet. I think everybody's just digesting everything they just heard. But you know, you guys see Tim's email there. So if you think of something after we sign off today, certainly reach out. You can obviously always email us, and we'll get questions off to Tim and his crew as well, if you want to do it that way. Oh, here is one that just came in. Where do you place the ultra probe on the cylinder for side load?
I usually place it on the rod end up near the seal where the rod is coming out of the cylinder. What I'm trying to hear there is the it's the contact probe, and what I'm trying to hear is the load on the seals. So anywhere I can get that's physically close to the seal, it would be the spot.
Okay, awesome. And then another question that just came in. So yes, I did record this. So I'll try and get it up on our website this afternoon. So if you want to email me to specifically ask for the link to where to view it, you can do that. Otherwise, you just on our website we've got it. So we'll have that up. And Tim, there's we tend to get a lot of folks asking about the actual slides. So I think, not sure if that's something you would share as a PDF or not, but I think requests like that, if you guys want to just email Tim directly to get any information like that.
They can shoot me an email. I'll see if I can get it PDF. I'm not quite sure how you do videos in PDF, but we'll.
Yeah, some of that stuff will probably have to go. But yeah, so definitely everybody be in touch with us if you need anything, or with Tim there. I'm going to take the screen back real quick, Tim, just to kind of go through a couple last minute things before we let everybody go. Mostly just wanted to let you guys know that we're going to do another webinar next week, a little more kind of self-serving, but we're going to be talking about our UltraProbe 15,000 and how you can utilize it for basically all the applications that ultrasound can be used for. So if that's something you guys are interested in, we'll have an invite going out tomorrow for that. So make plans to join us, and then we'll get something going for August, and certainly let you guys know about that as well. So Tim, thanks again for spending some time with us today, and everybody else that joined in. Really appreciate it, and hope everybody has an awesome rest of the day, and we'll see you guys around.
Thanks, Maureen.